So we're live, welcome back. We're going to be working with volume by cross sections today for the first time. So volume by cross sections, as the video is showing right now, is basically stacking a bunch of 2D images on top of each other in order to create a three-dimensional shape. So in this case, we've got right isosceles triangles. Those are isosceles triangles with a 90-degree angle here at the top corner. And then stacking on the base of a circle with a radius of 2 as we keep going from one side to the other. And we'll just keep stacking infinitely many of these isosceles right triangles on top of each other until we end up creating a three-dimensional shape. Okay, so that's the basic idea. So let me jump back into this again. Okay, so if I wanted to find the volume of this cylinder, then what I could do is I could split it up into a bunch of shapes that are circles. So here I have a bunch of coins. Each coin has a set radius and some amount of height. And if I stack the coins on top of each other, then our total amount of height will be however many coins we have times the height of each coin. And then each coin has an area, which is a circle. So that circle would be an area of pi r squared for this two-dimensional red space. So if I wanted to put all of that together, I could say that our volume is pi r squared, our area, times our height, where h is our change in height from the top to the bottom. If I wanted to write that as an integral, then I could say that our volume is really the area times height, or our volume is the integral of our area times our change in height, which would end up doing the same thing. If I integrate a dh, I'll end up with ah from our start point to end point, which would give us our total volume. Okay, any questions on what I've done here? Okay, then to take this a step further. If I wanted to integrate this crazy bell shape instead, then using the same principle, I can split this up into a bunch of two-dimensional circles, each one having an infinitely small change in height. So then I could get the area of each circle as we go up the bell, and then multiply by however much our change in height has been. So if I want this to be infinitely small, I could integrate instead. So that would add every possible area from the start point to the end point. So if I integrate our area times our change in height from our starting height at 0 to our ending height at however height our bell is, I'll end up with the total volume. Okay, any questions on what we did here? Okay. I'm going to go back and we'll do the same example that we had when we started. I'm going to get rid of all of our stuff from the other class. Okay, so from our video, we were stacking a bunch of isosceles right triangles on top of each other on a base that was a circle with a radius of 2. So if I wanted to model that, it would look like this. So if this is my side view, I'm stacking a bunch of isosceles right triangles. Isosceles means I have this 90-degree angle here at the top, on top of each other. If I was going to graph it from the top-down view, it would look like this. So we have a circle with a radius of 2. Redraw that just a little bit. A circle with a radius of 2. And then popping out of the page are these isosceles right triangles, like this. Which are paper thin. They've got this infinitely small depth to them. So it looks something like this. So this is, again, popping outside the page, just like we saw in our video here. We've got our circle with our radius of 2, and then popping outside the page are all of these isosceles right triangles we're stacking on top of each other. Okay, so this in yellow is our two-dimensional area, which from the side view would look like this. So here's all of our triangle in yellow. So to get the area of this triangle, I would still need to get 1/2 of my base times my height. Which in this case, if our triangles are isosceles right triangles, then I can split this triangle in half here. Which if I do, would split the triangle down this line here. So that would give me a y value on this side. And then popping outside the page, if I split that 90-degree angle so that I've got my y value, so from the axis to whatever my y value is over here, then that 90-degree angle will be split into 45-degree angles. So if this is 45 degrees, then this angle is also 45 degrees, which means this side here should also be the y value. Since our angles are congruent, our sides should be congruent. Which means our area would be 1/2 of our base times our height. Or my area is 1/2 of y times y. However, that's only half of the triangle from here to here. So this whole base of the triangle would be 2y. So I have to stretch double that distance. Okay, so here it is again. We have our y value, which is from here to here is our y value. If I double that, we'll get the base of the triangle. So another y gives us the total base of the triangle. Going up outside the page is also 1 y unit of distance. So the whole area of the triangle would be 1/2 of base times height, or 1/2 of my height of y times my base of 2y. Okay, any questions on how I got the area of this two-dimensional cross-section? Okay, I'm going to zoom in here. We also have an infinitely small depth to this triangle. That depth is our change in x. So as our x value changes, from the back of this, which is at x equals -2, to the front of this at x equals 2, we're going to constantly stack more and more triangles up outside the page. And then add all of their areas together to get the volume, like this. So constantly stacking as our x value changes from the start point to the end point. Each triangle has an infinitely small change in x. So that means that our volume would be equal to my area. Do this in color coded again. my volume would be equal to our area, which is here in yellow, times my infinitely small change in x. But I want to keep doing that for every possible x value, from x equals -2 to x equals 2, which means we can integrate. By integrating is repeated addition, so I will add all of the possible values of 1/2 times 2y times y times our change in x. Okay, our 1/2 and our 2 can cancel, so this is really just y squared. So my area is y squared, and my height is my dx. So that height is the depth of these triangles. And then we're moving from x equals -2 to x equals 2. Okay, so this is fine, except right now I've got y's here for our equation, and I want to integrate in terms of x. And I can't do that, I can't mix variables for integration yet, so I'm going to have to rewrite this y squared in terms of x so that we can actually integrate it. So I'm going to do that using our equation of a circle. So our equation of a circle is x squared plus y squared is r squared from algebra 2. My radius right now is 2 for the circle, so 2 squared is 4. And then if I want to solve for y squared so that I can substitute it in here, I can subtract x squared from both sides to get y squared is 4 minus x squared. So that leaves us with my area. Y squared is 4 minus x squared. So we can sub that in. 4 minus x squared times our dx. Okay, any questions on what we did so far? Okay, so that's the setup. That's the hard part, the geometry. Now we get to the easy part, the calculus. So I'm going to do this one by hand, and I'll call on people to help out. We are integrating from -2 to 2 of 4 minus x squared dx. If you did want to do it in your calculator, I've got your calculator steps here, but we're going to do it by hand. So first on the order is alien. Alien, if I want to integrate this, what's going to happen? Perfect, and we're integrating from -2 to 2, so I'm going to plug in my upper bound and subtract my lower bound. Over to Sarah. What's going to happen when I plug in my upper bound and subtract my lower bound here? Okay. You're right, I'm going to go ahead and write this in for everybody else, I think, just so we've got it for the notes. But why don't you keep going and I'll catch up. So that's 8 minus cubed over 3. Okay, so you said 8 minus what? For 3, and this is on this side. Okay, -8 plus 8 over 3. Okay, so I'm going to combine those. So I am subtracting a -8, so that means I'm adding an 8, so that's 8 plus 8 is 16. I've got a -8 thirds minus 8 thirds, so that's -2 times 8 thirds, since they're both the same, will give me -16 thirds. Okay, then I'm going to get a common denominator so that I can combine these. So that means my volume is equal to, if I get a common denominator over 3, this will be 16 times 3 is 48 thirds minus 16 thirds. which would give me 32 thirds. If you wanted it as a decimal, that would be 10.6 repeating, which is what we got in the calculator. Okay, any questions on what we did so far? Zoom out so we can see everything. Okay, I'm going to do several more problems, but I'm more concerned today about the setup than I am the integration, since I already know you guys can do the integration. So let me zoom back in on the setup really quick. Any questions on our setup? Okay, so let's do one more. Okay, for this one, we've got the base of a solid enclosed by this semicircle, y equals root 49 minus x squared in the x-axis. Cross sections perpendicular to the x-axis are rectangles with heights that are half that in the xy plane. So a plane is like a sheet of paper. In this case, our plane is the coordinate plane. So that's the whole x and y axis, this whole 2D part of the paper that we're drawing our x and y axis on. So the side that is inside the coordinate plane would look like this. This is perpendicular to the x-axis. Perpendicular to the x-axis. Cross sections that are perpendicular to the x-axis are rectangles that have heights twice that, so double the side that is in the xy plane. So popping outside the page right now, I've got something that looks like this. A rectangle such that the part of the rectangle that's popping outside the page has twice the height of the side that is inside the page. So let me color code this the same way we did last time. So this part in we'll say purple. Is my infinitely small change in x. And this part here in yellow is the two-dimensional area of our cross section. Okay. So let's see. I've got next on the order is Jana. Jana. What is this distance? For all of my cross sections.
Y.
Perfect. So that's the y value right now. And then we were told that the heights that are popping out of this page that make it three-dimensional are twice the height that's inside the xy plane. So if that's true, what is this distance?
2y.
2y, perfect. Okay, so that means my area right now of the two-dimensional cross-section should be what?
2y squared.
2y squared. My depth right now is dx. So what's my equation for the volume?
2y squared dx.
2y squared dx. Perfect. All right, over to Kelly. Kelly, what are the bounds of the integral first?
What was the question?
I need to know what the bounds of this integral should be. Perfect, negative 7 to 7. So that's my starting x value and my ending x value here at negative 7 and positive 7. Okay, and then I also need to rewrite this equation because right now I'm in terms of y, and we need to be in terms of x before we integrate so that I'm in the same variable as our infinitely small depth here. So I think I'm going to stick to Kelly because I just asked for bounds. So Kelly, one more. How can I rewrite this volume so that I have it in terms of x instead of a mixed y and x? Not sure. So we've got the base of our solid is a semicircle with this equation. Cool. Okay, so I've got that 2 as a constant. I'm going to pull that 2 out. And this is y squared, which means I'm going to square this square root. So I am going to write it out just so we can see it for the notes. But if I square that square root, the square root will go away. And that will allow us to have this volume equation in terms of x instead of in terms of y. So if I simplify this, this will be 2 times the integral from negative 7 to 7 of 49 minus x squared dx. Okay, did I get everybody on Zoom once? Yes. So let's go over to Skype. In Skype I've got Kenichi. So Kenichi, what happens when I integrate? Kenichi, can you hear me? Actually lost his picture. He might have dropped. Tommy, are you there? Okay, I don't think I have anyone in Skype anymore. So that brings us back to Aileen then. Aileen, what's going to happen when we integrate? Okay, from negative 7 to 7, and then I still have this 2 on the outside, so I'm going to leave that 2 on the outside here. I will have to distribute that in eventually. So I can choose to do that now, or I can choose to do that after I plug in these 7s and negative 7s, which I think I'm going to wait, because 49 is 7 squared. So if I don't multiply this in, then I can just rewrite these in 7s, I think. So let's keep going. I've got my volume is equal to 2 times. I'm going to plug in my upper bound. 49 by 7 minus 7 cubed over 3. minus my lower bound. 49 by -7 minus -7 cubed over 3. So 49 by 7 is 7 cubed, which is, if I remember right, I believe 343. Okay, somebody double check me really quick. 49 by 7, 343.
It's correct.
Okay, cool. Then I'm still going to leave our 2 out. When I go to add these, I've got 343 plus 343. So I've got 686. And then negative 343 over 3 minus 343 over 3, so that'll double it, is minus 686 over 3. I'm going to get a common denominator because I don't believe that reduces. So this is 686 by 3. So I've got 18. 24, 25. I don't think I did that right. Oh. I need to get more sleep. 686 times 3. Yeah, I did not. 2058. Okay, minus 686 over 3. Let's keep it this then. So I've got 1372 over 3 by 2 is 2744 over 3, which I don't think reduces. It does not. Okay. So our volume was 2477 over 3. Nope, 2744. 2744 over 3. Okay. Any questions on what we did for this one? Again, I'm less concerned with the integration part. I'm a lot more concerned with the setup, since I know you guys can integrate. Any questions on the setup for this one?
No.
Okay. Last one, then we're done for today. So slightly trickier. So I'm not just going to the x-axis anymore. The base of our solid is enclosed by y equals 4 and y equals x squared. So I'm going to write that really quick and possibly color code this. So here in red, I've got y equals 4. And then in blue, we've got y equals x squared. And we're told cross sections perpendicular to the x-axis are semicircles. Zoom back in again. So once again, perpendicular to the x-axis, so forming a 90-degree angle with the x-axis means we're going up and down here on the page, are semicircles. So once we pop outside the page, it'll look something like this. Little half circles. And again, our depth is infinitely small. So that infinitely small depth will be a change in x. And then here in yellow is our cross-sectional area. We'll keep stacking these semicircles on top of each other from x equals -2 to x equals 2. Now they didn't give us that, but that's when x squared would equal 4. X squared equals 4 if x equals plus or minus 2. Is our start point and end point because those are our intersects. Any questions so far on the setup? Okay. So we got the intersects. The next thing we need is I need to figure out what the area of this shape in yellow is. I believe we just did Aileen and Kelly. So I'm going to jump over to Jenna. Jenna, I need to figure out what this distance is here in black that's inside the xy plane for the semicircle. So if we know that this distance from here to here is always what? Who are we on? I've got Jana as next in the order.
Sorry, what was the question again?
Asking how we can get the black side of this semicircle that is inside the xy plane. So I need that distance. So to get there, how much is this distance here in red? 4. And how much is this distance here in blue?
X squared.
Perfect. Our y value, which is x squared. Okay, so what is this distance here in black then?
Minus x squared.
Perfect. Okay, that was the hardest part of all this. So our diameter of this semicircle that I need to get the area of, my diameter of the semicircle, is 4 minus x squared. If our diameter is 4 minus x squared, Sarah, what is the radius? Okay, I think you're coming in and out a little bit. It's not going to help because you're on Zoom. That's as loud as I can make you, unfortunately. I think you've got the right idea, though, because I know you at least divided the first part by 2. So this radius is going to be my diameter divided by 2. So this will be 4 minus x squared over 2 will be my radius. So if that's true, then what will the area of this whole semicircle be? Okay, Sarah, I'm going to try one more time. So, Sarah, what's the area of this semicircle if we know that the radius is 4 minus x squared over 2? Okay, so we've got half of a circle for this yellow part, if that helps. So if this is a half circle, then what should the general formula for the area be? Okay, I'm gonna grab anyone because I don't think Sarah's mic is working. So anyone, what should this area be?
One half pi r squared.
1/2 of pi r squared is perfect. And then we'll just need to substitute from our radius. So for us, our area is, I'm going to write pi over 2, so that's the 1/2 times pi, times our radius, 4 minus x squared over 2 squared. Okay, any questions how we got our area? Okay. I'm going to jump over here and we'll do some calculus. If all of that is true, then my volume should be equal to my area times my depth. Which, if my depth is infinitely small, then we'll go from a start point, which we said was -2, oh, I did that in orange, -2 to an endpoint of 2, and we had a depth of dx. So we'll substitute the integral from -2 to 2 of pi over 2 times 4 minus x squared over 2 times dx. Squared. So that was radius squared. Okay. So this pi over 2 is a constant. I can pull that out. Our volume is pi over 2 times -2 to 2 of 4 minus x squared over 2 squared dx. Then we're back over to Jada answered last time, so over to Aileen. What happens when I square this? Uh, 4 squared, okay, so that's 16. Okay, x to the 4th power, and that would be positive, I believe, so we've got a negative there. And then our middle term?
Minus 16, 8
8 x squared, okay. So I've got the 16 minus 8x squared plus x to the 4th, okay. And then on bottom? 4 dx, all right. So that over 4, I'm going to pull out that 1/4 that I'm multiplying through everything right now and just move that to the outside. So this will become, our volume is equal to pi over 8. So that's the 2 that I had on bottom times the 4 that I had on bottom. If I pull that out, becomes 8. Integral from -2 to 2 of x to the 4th power minus 8x squared plus 16 dx. Okay, any questions on what we did so far? Okay. Next is Kelly again. Kelly, what's going to happen when we integrate? Okay, x to the fifth over 5 minus,
4x2, no, 8x cubed over 3.
okay, 8x cubed over 3 plus
16x.
16x. And we're going from negative 2 to 2. So then we'll need to plug in our upper bound and subtract our lower bound. So that gives us got 2 to the fifth power over 5 minus 8 times 2 cubed over 3 plus 16 by 2 minus all of our lower bound. Okay, something interesting I'm going to throw as a side note. You'll notice for all of our problems so far, we've ended up subtracting the negative numbers. That's because all of the problems we've done so far have been symmetric about the y-axis, and if that's true, you can actually shortcut this by just doubling whatever you got for your upper bound. Since we're covering the same amount of area on the right-hand side as we are on the left-hand side of x equals 0. So you don't have to, but I'll show you what I mean. So I've got 2 to the fifth power, which is 32. Minus 2 to the third power is 8 by 8 is 64 over 3, plus 32. Okay, minus, if you look on the other side, we'll end up with the same values. Negative 32 over 5 plus 64 thirds plus 32. Negative, negative, negative. It's actually minus 32. Or will be. I haven't distributed that negative yet. Okay. So when I go to add these together, they'll end up doubling. So I've got 32 fifths plus 32 fifths is 64 fifths. Negative 64 thirds minus 64 thirds is negative 128 thirds. And then 32... Okay, why didn't that one work? Oh, this is a plus 16. Okay, so I just wrote it wrong. There we go. So negative 32, if I'm subtracting a negative 32, that'll be a positive 64. So everything doubled. And again, the reason for that is because the area that we were integrating is symmetric about x equals 0. So this area on the left is the same as the area on the right. How do I want to do this? I'm going to do this in terms of 64ths, so bear with me a minute. Volume is pi over 8. If I really wanted to do this by hand, I would split this up like this. I'm going to get my common denominator of 15, which is 3 times the 64 I already had, and I'm leaving this in terms of 64ths, which means this 128 is 2 times 64th. And then I'm also going to multiply by 5 in order to get my common denominator of 15, plus 15 times 64. Okay, so everything is now under the common denominator of 15, since the 64 is 64 over 1 if I wanted to write it as a fraction. Any questions on what I did so far? Okay. So really, this is 3 times something minus 10 times something plus 15 times something. 3 something minus 10 something is negative 7 something. Negative 7 of something plus 15 of something is 8 of something. Okay, then our 8 and 8 can cancel, so we're left with our final answer. Our volume is 64 pi over 15, which I don't believe reduces. Okay, any questions on what we did?
No.
Did some weird algebra tricks there at the end, but okay. So I will post the video and all of these examples up to the chat in case you want them for later. Our homework is 10 practice problems using the same idea, which will be due on Wednesday at midnight for this class. Okay, thank you for coming. It was a really long class and I apologize. But you guys did great. That was amazing.
Bye.
Goodbye.